Come on. There we go. Let me reshare my screen just in case. So 4.3 and 4.4 is still about maxes and mins because we're still in chapter 4. So the techniques for finding maxes and mins of a function kind of make up a kind of subset of mathematics that's called optimization. And that's because a lot of these problems, once we get into the contextual ones, are going to be something like we want to have the largest area or the largest profit or the smallest cost. And it's kind of like making the most optimal situation. So that's why it's kind of called optimization. But anyway, so we have two new functions. So remember in 4.1 and 4.2, that point won't go away. In 4.1 and 4.2, we talked about local maxes and mins and how to find them. Now we have a new type of max and min. So we have that a function f has a global maximum at p if f of p is greater than or equal to all values of f. So essentially it's the point with the largest y value. It's the highest point on the graph. And then a function has a global min, global minimum, yeah, if f of p is less than or equal to all values of f. So the global min would, of course, then be the lowest point, the smallest y value on the graph. So just like with local, now I said way back when we took the notes that local mins and maxes can also be referred to as relative maxes or mins, and I didn't use that word a lot. I don't think Wiley used it, but just in case. Similar thing here, sometimes absolute is used. So absolute max and absolute min. I think, again, your book, Wiley, and therefore I will try to use global more often than not. I sometimes do accidentally slip into absolute. I didn't really do that with local and relative because I usually use local. Sometimes I personally think of them as absolute maxes or mins, so I'm sorry if I flip-flop between the two, but they mean the same thing. So there's a couple different situations we can be in to talk about global maxes and mins. We can either talk about the entire function in general over the entire real line, or we can essentially just take a piece of that function over some interval, and we can either look at the interval including endpoints or not including endpoints. So we kind of need to find kind of three different ways to find these maxes and mins. So that's what we're going to do first. We're going to talk about how to find them, and then we'll do some examples. And we won't be able to finish today, so we'll have to finish on Monday, but we'll get as far as we can. So to find global maxes and mins, and I'll draw some pictures too to kind of help hopefully demonstrate what I mean by these global maxes and mins. I'll do that in a second. So to find a global max and a global min of a continuous function on an interval including endpoints, what we're going to do is we're going to find all critical points. So these start off pretty much just like we're finding local maxes and mins. We're going to find the derivative, we're going to set it equal to 0, we're going to see if it's undefined. So we're going to start off in a very similar fashion. But then, instead of using a sign chart, well, we're going to use a sign chart in one of the things, but most of the time we don't need one. Instead of using a sign chart, what we're going to do is we're going to plug in all the critical points and the endpoints into the original function, and we're going to compare y values because we want to know which one's higher than the other ones. And all of the global maxes and mins are going to be at one of those points. It has to be either at a critical point or at an end point. And I'm going to draw some pictures to try to demonstrate why. So I'm going to do two cases. And let's say that we're working. Why is this no longer erasing when I tell it to? Interesting. let's say that we're looking over some interval. So let me split this up at, we're just looking at a piece of a function from a to b and from a to b. So say my first function, I don't know, looks something like this. Oops. Now it's doing it. No, it's not. 1 second. Boop. Boop. And actually, let me lower that point down a little bit. Okay, anyway, so we'll go this way, and then that, and that, and there. And let me get rid of that underline of that original function piece. There we go. So if I'm looking at this graph and I just want to focus on local maxes or mins at it for a second, I have a local min there, a local max here, and a local min there. So I can still talk about local, but now if I want to talk about global, I want to know which one of these points is the absolute lowest point on the graph and the absolute highest point on the graph. So kind of my second local min, the one down here, notice how that y value is lower than any other y value on this function. So this one down here would be our global min. So that particular that local min also turned out to be a global max. Min, goodness gracious, what is wrong with me? Global min. And then that local max in the middle is also, again, the y value of that max is higher than the y values of the rest of the function. So that local max would also be our global max. So we would have our global max there. The other one on the left, the other red local min, is still a local min. It's still local, but it's not a global anything because there are some other points that are higher and some other points that are lower. So global extrema in any way. But the reason we have to consider endpoints when we're kind of just taking these kind of pieces of the graph is, what if I have a graph that looked, that went a little too sketchy there. Let me try to make it clear. Let's do, and then that's just, there we go. What if I have a graph that looks like this? Well, if I consider local maxes and mins, I do kind of have a local one right here and a local one right here. But if we want to consider the absolute highest and absolute lowest points on that kind of function piece, they actually end up being at these endpoints. Because if you look at, the y value of those endpoints, those y values are higher and lower than everything else in that interval. So actually, for this piece, the global maxes and mins didn't really appear at a general local max or min at all. We had a global min at an endpoint and a global max at the other one. Now you can also kind of have half and half, where one of them ends up being at an endpoint and the other one ends up being at a local. So it doesn't have to be both either in or the endpoints. But that's why we have to test both. We have to test the critical points because they could be the local ones and the local ones could end up being the global ones. But we also have to test the endpoints because once we've said that we're only looking over a piece of this function, the highest and the lowest point could then actually be at one of the endpoints instead of in the middle. So that's kind of why we have to do that. So hold on for a second in case anyone needs to catch up. And then we'll talk about the other two cases that we have. So the next case is very similar, where we're looking over an interval, but we're no longer including the endpoints in the interval. So we have an open interval. So let me try to leave that in there. There we go. So what's going to happen for an open interval is, open interval over here. So we're going to follow the exact same process as for the closed. And we will get to some examples of these today. So hopefully that'll clear up anything that's not quite clear yet. So we're going to follow that same process for closed interval, but Now, this probably isn't the official way to say this by any means, but I like to say that the endpoints can't win. What I mean by that is when we do our process for finding global maxes and mins on a closed interval, we look to see which y values are the largest and which y values are the smallest. And essentially, if that largest or smallest y value would have been in an endpoint, then you don't have that type of global extrema because we're not actually including the endpoints. So let me draw a picture. I don't know, my erase button isn't working. So say we're splitting this up between A and B again, and I'll do dotted lines this time to remind us that we're not including the endpoints. And say my function looked like, so I'll have an open dot as well to remind us that we're not including those endpoints. Say my function looked like this. So if I look at local maxes and mins for a second, I have a local min there, a local max there, and a local min there. So if I wanted to talk about global, well, that kind of first local min on the left is lower than every other point on the graph. So that local min would be our global min. But now I would really like to say that this endpoint on the left is the global max. But again, we don't actually include that endpoint in our interval, so we can't actually be equal to that endpoint. So what we're going to say is we're going to have to say that there's no global max. And now, well, maybe, let me do it up here, maybe. Say I tried to zoom in on that like a whole bunch. So here's our thing, and here's the endpoint, and here's the graph doing its thing. Let me try to make this obnoxious so it doesn't look like I'm trying to make that part of the function. So essentially, we can't say there's a global max because, well, maybe you would want to say, well, why don't we make the global max at, x equals, well, I need to, what am I doing? Hold on, give me 1 second. Let me say that I let a be -1 for the sake of allowing me to say what I want to say now. Say, well, why don't you just make the global max at -0.99? Well, no matter what value you give me to want to make the global max at, I can always find another point that's kind of, closer to the endpoint that would be higher than that value that you gave me. And we can do that infinitely many times. So if you were trying to argue that we could make it closer, I could always give you something that's closer than that. And we would never stop arguing because I can always find you a point that's closer, but not -1. So that's why there's actually no global max at all, because the highest point on this graph, therefore, technically doesn't exist. I know that might not make a lot of sense because there is this idea of a stopping point in our brains because it's, it stops at -1, doesn't it? But there are infinitely many numbers between whatever number you want to pick and -1 that I can choose from. So there would be no global max in that case. Anyway, hopefully that makes sense. And then we have one last case, and then we'll do some examples, where we're talking about the entire real line. So we're no longer splitting it into an interval, we're just talking about the whole entire function. Now, this one takes the most thought. I don't want to say it's any harder, but it takes the most thought. And I'm also going to need to squeeze in a lot of information on the side here. I should have given us a bit more space, but we're going to have to squeeze a lot of information kind of on the side here. But anyway, if we're talking about the entire real line, what we're going to do is we're going to find all the y values of the critical points. Sometimes it'll turn out that you actually don't need them, but you should find them in case you do need them. And then what we're going to need to do is we're going to need to use the derivative sign chart . Like what we were using for local maxes and mins. We're going to have to use the derivative sign chart to get an idea of the shape of the graph. And that's what we're going to squeeze in the information on the side really quick here. And I want to draw a picture. Let me draw a picture first. So say we had a graph, I don't know, it looks something like this. So if I want to talk about local, we've got 3 local extrema. Now that one local extrema on the right does end up being lower than absolutely anything else on the graph, so that would be our global min. But notice that kind of the ends of this function are going up forever in both directions. So since it's going upwards forever and there's no like place for us to stop this function, there would be no global max here either. Now, if you have the graph, that's obviously easy to see, but if we didn't have the graph and we want to talk about how to find it without the graph, what we can do is we can use that sign chart. And again, this is where it takes a bit more thought. So, and I gotta kind of squeeze these in here. I'm gonna try to make them as clear as possible. So here's kind of the options we have. Bad network quality. Well, USC get better network quality. I don't know what to tell you. I'm still on, right? Yeah. Okay. It's just telling me that it's bad network. Well, if things start looking weird, let me know. Anyway, woo! No, don't do that. So we have a bunch of different cases here. So what's going to matter is the, oh, it's lagging a lot. This is what they meant by bad network. Let me try to unshare and reshare. Boink. Boink. Oh no. Oh no. Oh my god, that didn't even work. Can y'all see my little number lines on the very right? Because I can't. Oh no. Let me try one more time. Alright, hold on. It's all frozen. You can see it though, Haley? Or maybe you were agreeing that it's frozen. I don't know. It's definitely frozen for some of y'all. It's fine for you too, Rachel? It's really frozen for me. Okay, that one's unfrozen. That one's still frozen. You could have seen it. Okay, so you can't see it now because I took it down for everyone. Let me try to bring it up one more time. It's finally unfrozen for me. The video stopped working. What? Oh, my little webcam. Oh, I don't care about that. Okay. Now I can see them, so hopefully y'all can see my little 2 number lines that I started drawing on the right. Oh, Lord. So what we're going to care about is we're going to care about the kind of very left interval and the very right interval. So I'm going to put these 3 dots in the middle of all my little number lines that I'm going to be drawing. Maybe it'll... I don't see my dots. Let me just draw some things, and maybe I'll just unshare and reshare, then give you some time to write them down. Oh, there they are. Well, I'm just going to keep writing now, because I've got 2 more cases I've got to talk about. So what I'm doing is, eventually, you'll hopefully see a bunch of number lines, and the 3 dots in the middle are just saying that I don't care what's happening in the middle of that number line. It can do whatever the heck it wants. I just want to care about the things that are happening at the ends. So we kind of have 4 cases here. 2 of them are kind of grouped together, and then the last 2 are kind of their own bit. And again, sorry, it's getting a little squished here. So we have a case where kind of that last interval at the left and the last interval at the right might have the same sign. They both might be positive or both might be negative. Okay, it looks like it's working a bit better now. And say I think about that in terms of my little like line segment things that I like to do. So if I was decreasing and then decreasing here and then increasing and increasing, So we have these little like line segments, but think about what that means for what the function's doing at the end. So like for the negative case, sorry, go away. For the negative case, essentially it would be going up forever on the left and down forever on the right. And in the positive case, it would be going down forever on the left and up forever on the right. So essentially, in either of those cases, where kind of the, ending signs, if you will, the very last one on the left and the very last one on the right, when they agree, there's going to be no global extrema at all. Because essentially you have one direction that's going downwards forever, so you're never going to have a global min, and there's one direction that's going up forever, so you're never going to have a global max. So that's what we mean by using the sign chart to get an idea of the shape of the graph. We kind of need to see what's happening at the endpoints. I do want to clarify, especially for anyone who knows calculus, in general, this isn't the full process. What we would technically need to do is we would technically need to take limits. But since we don't do limits in this class, we can't do that. So all of the problems that we go over in this class can be solved using these sign charts. But just know that in general, we would need a limit. So just in case you think I don't know what I'm talking about, this is technically a kind of modified way to do this for our class. But anyway. And then we have a case where essentially it has opposite signs. So say the one on the left is negative and the one on the right is positive. So if we draw little pieces, we would have been decreasing and then increasing. So if we think about what that means in the ends, that would mean that we're going up forever on the right and up forever on the left. So if we're going up forever in both directions, then we're never going to have a global max. But what's going to happen is we will have a global min somewhere in that middle. So we'll have a global min, but no global max. And then we have essentially the vice versa, where it's positive on the left and negative on the right. So we're increasing and then decreasing. So think about what that means for the end of the graph. We'd be going down forever on the left and down forever on the right. If we're going down forever, we're never going to have a global min, sorry. So this means we would have a global max somewhere in the middle, but no global min. So I know that was a lot of information to squeeze over there. Sorry about that. But that's essentially how those go. So when you're working over an entire real line, or I should even be careful, even half of a real line. So say you're just taking from 0 to infinity, as long as, if you were to think about it as like if one of your endpoints would have been infinity, then you need to use this idea of this sign chart. We need to figure out if global extrema can actually exist by figuring out what's happening at the end of the graph. Again, technically we would want to use limits here, but we don't know limits, so we can't. So hold on for a second in case people are still getting that down. And then we'll do some examples. Now note that it is possible to have multiple global minima and maxima because they would occur at different x values, but at the same y value. So remember, kind of the point here is we're looking for kind of the lowest y value and the highest y value. Well, if there are 2 points that have that y value, or more than 2 points, then they would all be considered the global max or the global min. So essentially, like say we had something, so to give a picture of an example that would do that, say we had some graph that looked like this. I drew it to the best of my ability. I think it's slightly off, but hopefully you get what I'm going for here. These 2 points here at the bottom would both technically be the global mins because they both have the same y value, or at least I was trying to make them have the same y value. So it is possible to have multiple global extrema. It's just that they occur at different x values, same y value. So I'll leave that up for like 5 more seconds before we go down to our example. So also, I think it's probably because I was trying to shove all this in before the exam. There's not as many examples as I thought. So we're going to take this first example and we're going to do it in a bunch of different ways, even though the notes don't do that. We're going to kind of come off to the side. So if you're using my guided notes, you might want to grab a blank piece of paper too eventually. And that's what we'll do to finish off today, is we'll essentially look at this first example in a bunch of different ways, because then the rest of them are contextual. There's not really any more generic ones that I put on here, and we'll talk about the contextual ones on Monday. But anyway, so say we have this, we want to find the global maxes and minimums of that function on the interval -5 to 14. So we're going to do this problem as stated first, and then we're going to kind of do it in a bunch of different ways. So to remind us what we're doing, the first thing is we need to find critical points. Find critical points. So remember, that's when we want the derivative and set it equal to 0. And see if it's undefined, we still need to consider that. So we have 3x squared minus, 18x minus 48. Oh, it's lagging a bit. Well, that one is. That one's not. Silly screens. There we go. So remember, I suggest kind of factoring out any common factors in whatever your derivative is. All of those things have a 3 in common, so I'm going to go ahead and pull it out. We're going to need to set this equal to 0. So personally, I would suggest factoring this. If you wanted to just set it equal to 0 and then use the quadratic formula, that's perfectly fine. But if we factor this, two numbers that multiply to -16 and add to -6 would be -8, +2. So if we want to set the derivative equal to 0, we would get, well, let me do it this way so that I have space. We would have that either 3 equals 0, which doesn't happen, x minus 8 equals 0, or x plus 2 equals 0. So we'll get x equals 8 and x equals -2. And we should just say, is this ever undefined? There's no denominator, so that's never undefined. Just like with the other ones, if you do have undefined, they're kind of places that you need to check. Am I lying? Because there are some ones that will make that very, no wait, because it's the original function. So you would have to check them, but if the derivative was undefined, it would also be possible that the function doesn't exist there as well. That's more outside of the scope of this class, so you wouldn't necessarily need to worry about that. All of our functions should be nicer than that. So anything you get from the undefined piece, you should just, essentially the next thing we're going to do is we're going to plug them all into the original function, and you would just do the same thing with anything that makes it undefined. Plug it into the original function, see if you get a number. In general, there are some things that could go really weird, but again, we shouldn't be working with any of those types of functions, I don't believe, if I'm remembering correctly. Anyway, so the next step, which is essentially the new idea, is we take all of our critical points, so we plug the critical points and the endpoints into the original function. So if you ever need to try to remind yourself where to plug in, remember we're trying to compare y values. We're trying to find the highest point and the lowest point. So we want to compare y values. So we would need to essentially find f of -5 because that's one of my endpoints. We would need to find f of -2 because that's a critical point, f of 8 because that's a critical point, and f of 14 because that's also an endpoint. One thing I'll do really quick, in case you don't know that your calculator is capable of doing this. instead of having to type all of those in multiple times, well, there's a couple different ways you can do it on your calculator, but I'll show you one of them. So let me get out of here really quick before I share this. There we go. So let me pop over here really quick. Ooh, that screen's lagging a lot. Come on, catch up with me. There we go. So say you wanted to find all of those points really easily. If you go to the y equals key and you plug in the original function, so I already have it typed in from my class before this, but if you type the original function into the y equals key, and I'll hold on for just a second in case someone's trying to do it. And then if you hit second graph, it'll bring you to a table. And then you can kind of just scroll through and find all the values really quickly. So like f of 14 I have right here is 360. And then we need, what was the other one we needed? F of 8. F of 8 will be negative 396. And then I can scroll up a bunch and get negative 2 and negative 5. So f of negative 2 was 104. And f of negative 5, ooh, too far, is negative 58. I will say if you ever want to use this, this isn't as useful for something like getting up to 200 because you have to scroll all the way up and then you have to scroll all the way back. But for things that are relatively close to 0, it's pretty nifty. So your calculator can do that if you didn't know that. But anyway. So what did I just say all these values were? We have f of negative 5 is negative 58, f of negative 2 is 104, negative 396, and 360. So once you've found all of the y values, you just pick the largest and the smallest number. So we've got, let me do it in a different color. We've got that the largest value is 360. And then the smallest value is negative 396. So the largest y value gives you your global max, and the lowest one gives you your global min. So we have a global max at, now with these, as opposed to the local ones, you usually list them as a full coordinate point. I mean, you've already found the y values anyway, so it's not any extra work. But usually the thing we care about more in the global case is actually the y value versus the x value. We care about the x value, but we also definitely care about the y value in this case, where with the local maxes and mins, we didn't usually care about the y value. Here, you usually want both. So that's what you do for global maxes and mins on a closed interval. What we're going to do now, again, I'm going to hold on a second before we get there, but what we're going to do is we're going to essentially take this, whoops, we're going to take this, oh man, how do I make that go away? Go away. There we go. We're going to take that exact same question and we're going to do it in the other two cases. So there was an open interval case and a real line case. So what I want to do is I want to do both of those cases for this same function. Specifically because, again, I think I was just trying to rush all of this onto the exam, so I didn't put any other generic ones on here because I wasn't thinking, I guess. But anyway, so give me 1 second. I'm just plopping it over into my OneNote because this isn't on your notes. But are there any questions on that before we do, again, the same function, so we've done half the work already. We're just going to see how the end of it would change if we kind of change the interval that we're looking over. I'll wait 5 seconds. Okay, so let's pop over here. Oh, I forgot to bring with me the original function. So what was the original function? That was x cubed minus 9x squared minus 48x plus 52. So I brought half of our work with us so that we don't have to do it again. So the first thing let's look at is I'm going to name it B. Let's look at the same thing. So we're going to find global extrema. but now we're going to find it on the same interval, but not including the endpoints. And again, we've done most of the work already. I'm just going to kind of show you the conclusion and the way the conclusion changes for these. So you do the same amount of work, you do the critical points, you find them all. We plug all of those critical points into the original function, which we already did before, so I'm just going to plop them back down again. So we found all of these y values, -58, 104, -396, 360. But when it comes to the case where it's an open interval, we still want to consider, you know, the lowest and the highest points. So we would still be looking at f of 8 and f of 14. But what we need to remember is that 14 was an endpoint. And since the endpoints aren't included in this interval because it's an open interval, we won't actually have a global max here then, because 14 would have been the global max, but we aren't including 14 in our interval, so there just won't be a global max. So essentially the conclusion here would be a global min at 8, -396, and no global max. So essentially, this is what I meant in the notes section where I said do the same process, but the endpoints can't win. What I meant is you do the same kind of idea and you find the 2 points that would be the global max and min, but if one of them was going to be at an endpoint, then you just don't have that type of extrema. And again, the reason for that is we essentially, like, once, you know, if we're hitting our endpoint of 14, the graph is doing something where it's coming, you know, really close, but then it's not actually getting to 14 because we're not equal to 14. And this is where I was saying, you know, no matter what point you give me really close to 14, I can find another point that's closer to 14 and higher on the graph than the point that you gave me. And we can keep going back and forth until the end of the world, because there's infinitely many numbers in there. So while 14 would have been a global max, since we're not including it, there's no global max because there's kind of this infinite fight for a value that's higher than the other. Are there any questions on that idea of why that is what it is? And then we've got one more thing I want to do. Well, maybe I shouldn't have put that there. Why is my little eraser button not working? I don't like it. All right, well then there's one more option we could do for this, and that would be to look over the entire real line. Define global extrema over the entire real line. I'll be honest, that's probably not how they would phrase it. When it comes to a generic function like this, they probably just wouldn't give you an interval. They would just say, find the global extrema of this function. But I do want to be kind of clear with the contextual ones that we'll be doing on Monday. They usually don't state the interval, but sometimes there's an interval kind of hidden in the context. But if there's no context, like this one, it was just, here's a function. If they don't give you an interval, then you can assume it's over the real line. So how would we finish this one out if it was over the real line instead of on an interval? So again, half of the work is already done for us. We would have had to find the critical points. But what we have to do now is we have to pull out that number line to figure out what the graph is doing kind of at those ends. So we would need to look at kind of that first derivative number line. Now, technically, I also said find the y values at the critical points, but we do have them from the other parts that we've done, so I'll skip doing that again. So, sorry, scroll back up. So just like with local maxes and mins, we plop those guys on there, we choose test points. We find whether the derivative is positive or negative. I'm going to kind of breeze through that part because hopefully you would know how to do it. So if I plug in -3, I should get a positive. If I plug in 0, we'll get a negative. If I plug in 10, I should get a positive. And do be careful, since we're talking about the number line again, we're now plugging them into the derivative. If anyone wants to see more work on that, let me know. But again, kind of that was stuff we'd already talked about, so I'm kind of breezing through it. So that would mean that our function is increasing, then decreasing, then increasing. So think about what that means for kind of the ends. It's going up forever on the right and down forever on the left. So since it's going up forever in one direction, that means there's going to be no global max. And since it's going down forever in one direction, that means there's going to be no global min. So this just has no global extrema at all. No global extrema. And that is, again, because we just found kind of what that graph, maybe I shouldn't say what it looks like because it's so rudimentary and not exactly what the graph will look like, but we have the idea of the basic shape that we get from using that first derivative number line to tell us if it's going upwards forever or downwards forever in whatever, on whatever side of the graph. And then we can determine whether or not global extrema can even exist. So one thing I need to say a bit more about this. Any questions on that before I talk about a similar thing, but in more generality? Okay. In general, for questions like these where it's over the entire real line, if, maybe I should clarify and say global extrema. If global extrema can exist, so essentially so the only time they can exist is, oh my goodness, the only time global extrema can exist in the real line situation is if it goes up in both directions, in which case there will be a min, or if it goes down in both directions, in which case there will be a max. So if you're in either of those situations where global extrema can exist, they will be at one of the local extrema. So what you do is you find and compare y values for the critical points. And that's why I said in the kind of notes section of this to find the y values of all the critical points, because if the extrema can exist, it's going to be at one of those critical points. And that's the point where it's just like, okay, you have your two values that, well, in this case, it would have been two values. You have your values that you're comparing, which one has the larger y value or the smaller y value, depending on if you're trying to find the max or the min. So all of these have this kind of idea of comparing y values. It's just that sometimes you don't have to do it if you're over the case of the real line. So the real line case is the only one that gets a little weird, where we have to pull out this first derivative number line again to kind of see what the see what the function is doing at the ends to see if the extrema can even exist. So we just did one question through all three different types of situations you can be in: closed interval, open interval, entire real line. Questions, concerns on any of that? Okay. Okay, I'm not seeing anything. So 5 minutes is not worth trying to jump into the next contextual problem because they can be a little bit longer than the other ones. So we'll save all of that for Monday. Might even take a little bit into Wednesday, but anyway. So we'll do the contextual problems on Monday. Those ones, they have a similar process, but sometimes it can have one extra little step in it. So we'll need to talk about that. And other than that, we're good to go. Remember that chapter 4 homework was pushed back until November 2nd. So you still don't have anything that's due on Monday because we still haven't finished yet. So we'll hopefully finish 4.3 and 4.4 up on Monday, and then move on to chapter 5, which is a completely new topic. So anyway, I'm done babbling. If you want to stick around, if you have any questions, feel free to stick around for a little bit. Otherwise, have a great weekend. I'll see you on Monday. Yeah. I'll stop recording.